Thank you so much. So I will try to entertain you until the lunch.
Exactly.
Okay, good. So last time, yesterday I introduced these two aspects of studying functions, random functions of very many variables. One would be the topology, the second would be the dynamics of optimization if you want to go down. And remember, we chose a very simple random function, which is a polynomial, homogeneous polynomial of degree p, random homogeneous polynomial of degree p, which is the same thing and as a prominent example of a Gaussian isotropic field on the sphere, or which is also called in physics a spin glass. Okay, a p-spin spherical spin glass. And remember, we had this following picture that I will put here. So this is the energy level. I could do that for the temperature, but it was the same thing. This is what we understood from the topological thing. The average of our energy, this random polynomial, was 0. That's the average. The weight was normalized. It's not important, but that's what I write here. The fluctuation was inside square root n. We were in dimension n. So if you take a typical value of this, the typical values of these energies are here. And then the bottom value, the ground state, the minimum, the thing we wanted, was at a certain constant, which I call E0. Right? And then there was somewhere here and something called still very low. So here I should, I cut that because it's whatever. And remember that all in this region here, so this is very low. This is in the regime of extreme values. The minimum is at minus constant n. In this regime, you had exponentially many local minima. And above this, you had no local minima, right? And in fact, no critical points of finite index. But you had, above this, you had exponentially many critical points, but of a diverging index. So if you take a point, in fact, the index and the depths are related. If you take a point at an energy level which is 0, let's say, or near 0, then the index will be essentially n over 2, right? Which means n over 2 directions are going down, n over 2 directions are going up, okay? If you take a point here, the index will be n over 3. You have less directions going down, right? Good. So that was in fact, there was an energy level somewhere here, which I call E static, or T static. And in this regime, here it's not temperature, but in this region here, you had the wells that carried the Gibbs measure in the 1 RSB phase, 1 replica symmetric working phase. That was the static transition, and that corresponded to the dynamic or shattering phase. So in this, if I want to speak in terms of shattering phase, this region here was a region where this was 1 RSB here, and this one replica symmetric, but shattered. All right, remember what that means? That is, the Gibbs measure was here made of rings, exponentially many of them. And so that's why if you took 2 of them, they would be naturally orthogonal, so their overlap would be 0, which says that the order parameter is not the order parameter, right, in fact. Because here the order parameter, which is the distribution of the overlap, does not capture this. But this topologically complicated region here has consequences on dynamics, as I will say. And so here, this thing here corresponded both to this shattered thing and to the dynamical transition, as I mentioned, which was the place where the thermalization time would diverge. Okay? So that was what we learned last time. So just a few things about, I'm coming back to dynamics now. So what we can prove, of course, and we did, was that the important thing is, still here, so let's think about dynamics. You start with a point, let's say, taken at random, to do like physicists look at thermalization time, right? You take a random point, not informative thing, because that's what will happen in data science when I go to statistics, let's say. You don't know what to do, so you start with a random thing. If you start with a random thing, you will be essentially at this level. And the question is, how do you get down there, right? So of course you have all these wells. Remember the structure, you had these wells, the Gibbs measure was concentrated on those things. Here you had exponentially many rings like this and so on. And you had a few climbing up here. So of course when you start from here, you could be very unlucky and fall in one of them, but this does not happen essentially. So what happens is you will go down to somewhere above this level threshold quickly. But that's already something interesting. So this is what we will concentrate on. During this descent phase, this first phase that we call descent phase, which of course is not what you use typically in physics, but that you do in machine learning, the system manages to go deeply and ignores completely the critical points of all index. So in this phase, in the initial phase, you start from here and you go down to somewhere here in finite time, very quickly, even though there are a quantity of critical points of diverging index. There may be a lot of wells that come here. You just don't see them. So in this descent phase, and you go from 0 to something which is in the same scale as the absolute minimum, right? It's a constant time n. So you go maybe to, I don't know, 70% of the best performance possible in a very short time, right? At the descent phase. And the complexity here plays no role. Okay? It's as if you could replace your complicated landscape by something totally flat. It would change nothing. I mean, of course, with the force going down, but it would change nothing. Okay? So that's something, I discussed this yesterday with some of you. If you read anything on optimization and things coming from people who do optimization for a living in finite dimensions, or even from physics, the first thing that everybody thinks, I'm sure you do, I did, is that the difficulty is the topology. Why would an algorithm not work? It's because it would get stuck in a well, right? That's what we all think. This is crap. This is not what happens in high dimension. The problem, in those time scales, what I told you yesterday was the contrary. So I was saying, of course, if you consider the time scales of physics, exponential in n, the time it takes to reach equilibrium, then of course you explore those wells, you find them and you get out of them and you find another one and you age and all that. But in the short time scales, which are the ones that are important for statistics, this is why I'm insisting, in the shorter time scale, you just don't see those things. And so why is that? So the problem is not to exit the traps in short time scales. Okay? So why is that? Why don't you ever find those things? It's because, in fact, it's again an entropy question. You may have exponentially many wells, whatever, but still the volume they occupy on the sphere is small. So if you start at random, finding a small region is hard. So the real problem is, why do you not have to think about exiting those wells, even though they exist? It's just because you don't find them. It's hard to find them, and once you find them, it's hard to get out of them. Okay? And you do find them, of course, but in much longer time scales. In the short time scales, you just go zoom down, okay? But the real question is, so if you're happy getting 80% as performance, getting somewhere here, right? This is still a fraction of what you want. Then you can do that very easily in a very short time. But if what you want is to get really the minimum, then it's harder. Okay? So in this descent phase, and this will be valid in many models, in high dimension, the problem is not necessarily to get out of deep wells. Because in high dimension, it's hard to find the deep wells. Okay? So, and yesterday I mentioned also the question of metastability. So let's just say, so this level that I call E infinity, which is also the E dynamical or shattering, this is not the threshold for metastability. The threshold for metastability is above. And this is what I mentioned yesterday. So Barra, Burioni, and Mézard in '89 predicted that the onset for metastability happens higher. Okay? And indeed, for the temperature lower than this temperature, there are exponentially many metastable states. And we proved that at least when p is larger than 4, there exists exponentially many rings, like we had before, centered on the deepest local minima with exponentially small Gibbs mass. So they are tiny, but such that the probability that the Langevin dynamics, if you start from there, the Gibbs measure starting from one of these bands, escape this band fast, so the probability that you can exit this thing quickly is exponentially small. So you really have metastability, right? It takes, so what I just said is you never find those things, right, if you start from random. But if you do start from there, then escaping is long. Okay, that's what this says. Okay, so all that is physics, enough with that. Spectral gap is exponentially small. That's what we know, which means, okay. So now let's go to the first example of statistics, the one that will make the link between the two. Okay, so that's, forget spin glasses. We have, what I'm talking here a priori has nothing, talking about here has nothing to do with spin glasses. So that's a different question. It's a pure, simple questions of statistics. So you take, you have a, here you have a vector v. So this is the simplest, stupidest thing of PCA. You all know what PCA is normally, principal component analysis. That's the first task of statistics in any class, including not math or physics, in econ or whatever. I give you the PCA, principal component analysis, I give you a vector that you don't know, and what you have access to is this vector in a noisy version, right? You have noise added to it, and you want to find the vector. So you know how to do that. You do regression, and that's it. But here I complicate the matter a little bit, because what I have access to is not a vector, but it's a vector to the tensor power p. Okay? So when p is 1, this is a vector. When p is 2, it's a matrix. When p is 3, it's a tensor, a cube of numbers. Okay? So think of it, just to think v, this unknown thing, because of course the statistical task is to find v. Think for a minute that v is just the vector e1, the first coordinate, or the first vector, right? 1 and all zeros. Of course you don't know. When you take v to the p, you get a cube of numbers, of size n by n by n, where everybody is 0 and you have a 1 in the corner. Okay? So that's your signal. That's what you want to find. And then what you have access to are those tensors, which is this vector plus noise. The ZIs are noise. Let's say IID centered tensors, right? Gaussian, if you, but I'll choose them. All right. So I give you a sample of tensors where you have noise everywhere, but there's this signal somewhere. Okay. And of course, I could change the variance of the noise, but here instead of changing the variance of the noise, I put a parameter lambda here, which will be a signal to noise ratio. When lambda is large, you have a lot of signal and little noise, and the other way around. So when lambda is 0, you have no signal. Okay? When lambda is very large, you have a lot of signal. All right, and so that's the signal to noise ratio, and the objective is, of course, to detect and to recover, which means estimate v. So detect means you have this sample. I called it M, so you have an M sample of these tensors. That's what you have as data. And the first thing before even estimating is detecting. Detection meaning there is a signal somewhere. Okay? And once you have detected, you may want to estimate. Right? So detecting means this is not just an IID sample of noise. There is something in it. And then once you have detected, you may ask to estimate. What is the vector? So here in the example I'm giving, the vector is just 1, 0, 0, 0. Okay? So, of course, you could ask the same question, and this has been studied. Of course, when the signal v, instead of being a rank 1 tensor like here, it could be a small rank tensor, a rank 17 tensor. Okay? And same question. All right? Very simple statistics question. Okay? You'll see what that is, right? So you have a sample of, let's say, 3 tensors, so cubes of numbers, right? Random numbers. And you want to detect if there's a signal in it. And if you detect there's a signal, you want to estimate the signal.
Okay. One question. So here what you would have would be the T's, but do you also have the statistical information on the sets? Or do you
Yes, yes, of course. You have a sample. Let me go there. So the noise is Gaussian. Let's say we assume for the moment no prior information on the spike, V, the unknown vector, which is, let's say, unit. So it's just a vector in the sphere, Sn minus 1. So which means that the prior, if you want, is just the uniform measure on the sphere. And then, so here are some references. And so you have this sample of IID of size m, let's say, of this V, lambda, whatever, V to the P plus noise. And so the first question is detection. So I give you this thing, you have m such things. Can you detect if there is a signal or if it's just noise? All right. So that's called the IT threshold, the information theory threshold. Is it possible to detect the signal? So that's what it means. The total variation distance between the distribution with a signal to noise ratio lambda and the distribution with no signal to noise, pure noise, is this going to 0 or not? Right? Because maybe you can't detect. Right? We'll think that we can always detect, but maybe you can't. So question 2, if you can detect, so that's an information theory type problem. Right? I have the sample, can I detect if there is something? Once you can detect, you can ask a statistical question. So recovery. Okay, I detect that there is a signal, can I recover it? Okay, maybe partly, maybe 60% of it, maybe fully, who knows? So that's a statistical question. And then, so of course, what would make that possible? What are the parameters you have in your hand? One is, of course, lambda, the signal-to-noise ratio of your problem. The largest the lambda, the easiest these problems are, the easier these problems are. And of course, you also have m, the size of the data, the size of the sample. And of course, n, the intrinsic dimension. Okay? So there are different regimes on these variables which tell you that you can detect, and once you can detect, maybe you can recover. Or maybe you can recover partly. So the question is here, when you do this question 2, yes?
Sorry, can you explain again the difference between detection and recovery?
Yes, in detection you have no statistical procedure. I'm just asking, I have the law with a signal and the law without a signal. Does their distance, let's say in total variation, go to 0 or not? This means, which means that the total variation distance is a soup, if you want, on all possible statistical procedures. It means if you're the god of statistics, would you find a way to differentiate between those two? In step 2, you've chosen a statistical procedure. So let's say maximum likelihood for statistical procedures for babies. Above what threshold for the signal-to-noise ratio is the estimator of the signal better than random? That's the statistical question, right? And when is it converging to the true signal? That's called strong recovery. The other is weak recovery. Okay, when you can do better than random. Okay. Question 3, of course, which is the important one, is computational. Now the question is, okay, you have a statistical procedure that will give you something which is a good estimator. Okay, but typically in a statistical procedure, you have a soup, an in for a variational problem to solve. So the question is, the next one is the computational one, the algorithmic one. So the algorithmic or computational threshold, right? So you choose first a statistical procedure. So first you check that you're in a regime where you can do something. You are above the IT threshold, the information theory threshold. Then you choose a statistical procedure, that's up to you. So this statistical procedure could be maximum likelihood, it could be to build a neural network, okay, with a certain architecture, okay? But then the next thing is computational. How hard will it be to do it, right? So pick a computational algorithm. Let's say you want to find a maximum likelihood. So you take an optimization algorithm like gradient descent or stochastic gradient descent. For what signal-to-noise ratio does it recover the signal? In short time scales. That's the crucial words. We are no longer physicists here. In physics, when you study our spin glass here, going to the bottom of it can take exponential n. We don't want that, okay? Because here, remember, n will be very large. So you don't want your algorithm to take 10 to the 10 to the 9 steps to work, right? Or if you try to sell that to Google, they will laugh at you, okay? So that's a different problem than the one from physics. We want short timescales. Okay, so if you remember our situation here where there was no signal, where it was pure noise, in short timescale, essentially we could get down to somewhere around here, right? If you started at random, which is already not so bad, but certainly not here. To get here, you needed exponentially long timescales. Okay? Yeah.
When you say short time, it's
for the moment, I'm not precise, but indeed it will be even linear in n or polynomial with small power or something like this, but not exponential. Okay. So there are three questions, right? IT question, statistical question, and then computational optimization question. All right? So let's take first the IT question for this very simple tensor PCA that I asked you, right? Very simple because it's rank 1. You have just one vector to find. Doesn't seem like very difficult. So in fact, there is a detection threshold. If you take a proper normalization, let me not get there because it's always a pain. I will fix the normalization by this. There is an IT threshold, which is positive. Let's say 1 here. So what does that mean? So lambda, remember, with the signal to noise ratio. There is a region where you have a signal, lambda is positive, but less than 1. I just fixed 1 to be the threshold here, in which the distance in total variation between the distribution of the tensor with a signal or without a signal goes to 0 when n is large. It's entirely a large n phenomenon, of course. So this means, even if you're the god of statistics, there is no way to detect the signal. You have a signal, and there is strictly no way to find it. Not only to find it, we're not even trying to find it, only to know that it's there. Okay? The distribution of this random tensor, I was telling you, with the V or without the V, in fact, these two distributions are essentially the same. Right? Their distance goes to 0 in total variation. So there's no way to distinguish them.
So n is going to infinity, but m is already. So
I'm sorry?
M.
No, there is no sample size. No. There is no sample size. The question here is before statistics.
Yes.
It's just, you're God, you can do whatever, you still can't. Okay? There's no way. Those two distances go, the distance between these two things go to 0. So you have no procedure saying the total variation distance goes to 0 means there is no way to distinguish those two. Don't even try.
Out of curiosity, how this lambda or this threshold behave with p? Does it get... okay, maybe.
Now I don't know. I really don't know. I forgot. I knew it yesterday, but I forgot. Okay, I can tell you. Yeah. That's why I fixed it at 1, just to not remember that. Okay.
One question?
What?
Sorry,
yes.
Just to clarify, you can have as many samples as you want and you...
There is no sample here. The question is before sampling. The distribution with a signal and the distribution without a signal, they are essentially the same. Their distance in total variation goes to 0. When you integrate again this distribution, whatever you want as a, let's say, continuous bounded function, the two integrals will be going to 0 when n is large. So this tells you don't even try. And it's important to understand that. This is typically something coming from the pervert side of science, which is theoretical computer science, right? Which love to prove some things like that, which are, it doesn't work. And there's plenty of that in theoretical computer science.
And n being large?
I've seen just a second. Yes?
What's n again?
N is the dimension.
Okay.
So your tensor, my tensor here is a cube of numbers. Let's say a 3 tensor, it's a cube of number of n by n by n. Okay, so n is very large. These two, and this is what we are doing here. Big data is n large, right? So in this regime, you cannot distinguish. Yes?
No need anymore. I just want to re-clarify. N means the dimension has nothing to do with the samples because maybe there are...
No, for the moment there is no sample. N is the dimension of your tensor. I will introduce the sample now. So now, let's say you are above the detection threshold, the IT threshold, so you can begin trying to do it. So you choose a statistical technique. And that's up to you. So let's choose the baby statistical technique, maximum likelihood. Right? The thing that everybody's learned, and the first thing you try every time you have to do something. So let's take maximum likelihood. So if you do maximum likelihood here, then there is a threshold, lambda MLE, a threshold for maximum likelihood, which is in fact the same as the IT threshold. So here you have, if I put lambda, the threshold here, the strength of the signal, have 0, then I have a threshold. Then if I take a statistical procedure, the threshold for any given statistical procedure should be above this one. It cannot work below. Here in this case, they are the same when I take the MLE, which means that the MLE is optimal. As soon as something works, as soon as you can detect, as soon as you can distinguish these two things, then you can do it with MLE, right? Which is good news because MLE is the simplest thing you can do. Okay. There are many other things that would work, but let's stay with MLE because that's where I want to make the link with what we did before.
Tell us what you mean by partial recovery. This means that you can...
So I will explain in a second. Partial recovery means I have this vector, so let me explain that a little bit. You want to recover a unit vector in dimension 1 billion, all right, in very large dimension. Let's say so a point on the sphere in very high dimension. If I could say, here's an estimate, I pick a vector at random. I cheat. Then what will be the typical angle between those two? 0, because if you take 2 points at random on the sphere in high dimension, they are orthogonal. Okay? Now, when I say partial recovery, it's doing just better than that first. Right? So you have a sphere in high dimension. Again, this picture is absurd because a sphere in high dimension does not look like that at all. If you think of a sphere like this, you cannot see it in dimension large. But let's say, as I said before, that this is my E1, that's my V, my unknown signal, the North Pole. If I cheat. My boss told me estimate V, and I did something else, and I say, here's an estimator, which I chose at random. If I choose it at random, it will be here at the equator. So better than random is to be able, for instance, to find something here, right? Where on this latitude, right? This is better than random. Okay, that's partial recovery. Full recovery is, of course, to find something where this thing becomes very close to V. Okay? All right, so I'm saying to do partial recovery, the threshold is the same. That's a piece of luck here. Of course, as I said, this is not how you should think. People who have already heard that saw this picture. This is an absurd picture of a sphere in high dimension. If you want to think in high dimension, it's hard, of course. So here's how you should think. These two things are the two hemispheres, and this is the equator. Right? Why do I write it like this? It's because, in fact, the measure of a hemisphere, if you normalize the measure to be 1 for the sphere, the measure of a hemisphere is exponentially small in n. Right? So the hemispheres are tiny. Everybody is at the equator. Okay? That's an obvious large deviation result. If you think a minute, it's trivial. Okay? So this is how we should think. Right? Good. So so when it is possible to detect so what this says is that when it is possible to detect the signal, when you're above the IT threshold, in fact, in this very simple case, it's possible to recover it partially by the plain vanilla method, by MLE. Okay? So this question 2 is the question where complexity, topological, blah, blah, is the Katz-Rice formula that I mentioned before is useful. Right? Because I told you, what is the random function now? The random function we are looking at here will be the log likelihood of this problem. Right? As I mentioned, the log likelihood would be you have a sample. Now imagine you have your sample. You have a random function, which is the log likelihood on this thing. Okay? And then you want to minimize it with a negative sign. Okay? So the complexity of this function has been studied. Here are some results. So, but I will come back to that. So is this function, so I didn't write the log likelihood. But the question is, the log likelihood function will be complex. Right? We'll see that. Okay, now let's talk about the gap. So for the moment, I've looked at the first two questions, IT and statistics. In this case, it just happened that statistical threshold and IT threshold were the same. Now I'm talking about a gap. So now you could look at the computational thing. We're doing maximum likelihood. We have to find the maximum of the likelihood, right? So this is now an optimization problem. And in this optimization problem, I have a random function of many variables, right? The log likelihood. Okay, so the simple optimization algorithm, the standard ones, to find the MLE, to find the maximum likelihood estimators, whether you take gradient descent or Langevin, because you're a physicist and you believe that Langevin works better, and it doesn't, and SGD, because you're a computer scientist and you know that SGD is so much better, and it doesn't. They all work when in short time scales, when the signal-to-noise ratio is larger than this n to the p minus 2 over 2. So look at that. It means that this was 1, and then you have n to the p minus 2 over 2. So let's take p equal 3. This is square root n. There is a huge gap. Again, if your n is 10 to the 9, this is 10 to the 3. There's a huge gap in amount of signal-to-noise ratio that you need. In this big region here, your statistics problem works if you were the god of optimization, but you're not. So if you do an algorithm of optimization, there's a huge region where your algorithm will not work, even though it should. Okay? So this is called the computational to statistical gap. Right? You have a gap between statistics and optimization. All right. This threshold is also the threshold for many other algorithms. So here I'm talking about the simplest thing, the thing you would try. You build your likelihood function, you optimize it by whatever, SGD, GD, Langevin. They all fail at the same place. But you could do things which are less like that. For instance, you could use things that come from spin glass things, which are supposed to be much smarter, like approximate message passing, and the threshold is the same. Okay, so there is something happening there. Okay, so this is what I want to emphasize. Now, let's continue. There are less naive algorithms which works until the threshold p minus 2 over 4. These are algorithms that are good for theoretical computer scientists, but nobody in the industry would try it because they are much less easy to implement. So, for instance, they include semi-definite relaxation in the sums of square hierarchy. This was work by Afonso Bandera. And the Kikuchi hierarchy spectral algorithm, I give some references here. The replicated gradient descent, that was done by Giulio and his collaborators. Or the tensor unfolding algorithm, which goes back to Montanari. Well, I made a spelling mistake. It's Montanari without the second N, and which was proved rigorously with Jiaoyang Huang and Bryce Huang a few years back. So let me explain just what this one is, just so that you see that we're no longer in optimization. You do the following. Tensor unfolding is, I give you, so you have this random cubes, right, of numbers. Let's say if p equals 3. So it's n by n by n, right? Now you can unfold it and make it a matrix of size n squared by n. You see, you take this side of the cube, you put it there, this side of the cube, you put it there, etc. So it gives you a long matrix of size n squared by n, right? Now you compute the singular values of that, which means you take this n squared by n matrix and multiply it by its transpose, which gives you an n by n matrix, right? And then you look at the eigenvalues of this thing, which is the singular values of this. So you unfold a tensor, you look at the singular values, right? And then there is this spectral transition in random matrix, to which I will come back, which is called the BBP transition, which tells you that you have a signal now. Remember, you had this corner in your cube where you had a 1. Everything else was pure noise, and you had a signal somewhere. You had 1 lambda plus noise. Okay? And the question is, when you do all this, can you feel it spectrally in the spectrum of this thing? And there is indeed a spectral transition, which is called BBP, which says something happens. You have an outlier coming out of this, and the eigenvector corresponding to this outlier eigenvalue will be close to V, the signal. All right? That's the tensor unfolding. And this works above n to the p minus 2 over 4. So you still have a gap between this and that. Okay? And in this region, you have plenty of smart algorithms like this, which are not the kind of bread and butter optimization, but it stops here. Nobody knows how to go down this, below that.
Is it partial recovery?
No, now this, when you are with a very large n, it's not partial recovery, because when lambda is very large, this radius here that you get, for instance, in, let's say even here, when you take the gradient descent, this thing comes, when lambda is large, this thing goes there. So in this whole regime, when n diverges, you have full recovery. Now the question is, who is speaking? Oh, yes.
So are these statements about the worst case possible of the algorithm?
No, never. I'm not doing that. This is serious things, right? That is, you try to get, you don't try to prove that things don't work, like we did in spin glasses if you start in, in the wrong well or whatever. You start at random, a non-informed initial condition. Because of course, of course you could do, so what does it mean in this picture? This is where you want to end up. You start at random. If you start at random, where do you start? Here, right? And the question is, can you climb up here, right? Of course, you could start with a warm start. If somebody tells you, I know, I can start here, right? Then the algorithm will be very fast. You don't need n to the p minus 2 over 2. But of course, to understand why, look at this picture. If you start at random, it means you start somewhere here. If you start with a hot start, it means you start here. So yes, going down should not be too hard. Okay?
So,
yes.
I think here maybe it's useful to say something about the estimation procedures, because
I just said it's
no, the minimization approaches, what statisticians call M estimators. That's what you're discussing.
No, that's not what I'm discussing. No.
But the usual way to do PCA is not to minimize something. It's to look at the largest eigenvalues, and so that's an L estimator. Yes. So it doesn't correspond to a
Okay. I just said all that. You just didn't listen. All right? So first, the first thing I was saying were SGD, optimization. But now all this describe, and then I mentioned approximate message passing, which is not optimization. But then, look, this is not optimization, and the last thing I just described is precisely what you're saying, the tensor unfolding, except that what is the eigenvalue of a tensor? Right? So one way is to unfold the tensor, make it a matrix, and then you have eigenvalues, and then you have the BBP transition, okay, the spectral transition you're mentioning. And it still fails here for a very simple reason. Nobody knows anything that works in this window, right? Some people may, now let's go back to the hard part, the theoretical computer scientists. Some people believe that in fact one should be able to prove that there is no way to do it. If you could do that, you would prove that P equals NP or whatever. I won't go there. Okay?
Sorry, so the exponent that you get here, so this growth, is the one that you can prove,
yes,
or the one which is
yes,
the real one?
For all this thing, it's proved.
Yeah, so
No, but you prove, you prove, okay, and I get your question. You prove that it fails below it and that it succeeds above it.
Okay.
So that's not the question. So for the moment, nobody can beat this n to the p minus 2 over 4. You've heard me say maybe you should try. Don't try. Because every time somebody tries, it fails, and some people have very deep reasons to believe that you can't. Okay, so that's probably not a good enterprise.
So to be really caveman, can you learn something about going below the equator, trying to really be as worse as possible? So we want to go from equator to the top, yeah, but I can also go below the equator. I know I'm being
No, but if you do anything like this, you have a drift that will push you there. Going there is, of course, very, very. Of course, if you put your signal here, you will go below the equator. That's symmetric.
Yeah. Okay.
So. Okay. So let's look at what. Let's be a little more precise. Let me come back to the plain vanilla thing, the MLE. Okay. And oops. So let me write what this is. So the estimator V, you estimate V with the maximum likelihood, you solve the following optimization problem. You construct a loss function, this R, depending on M, if you have an M sample. And what you have to do is look at this. Y, so let me explain. What is MLE? Your thing is Gaussian. So you can write the law of your system, right, which is Gaussian. When you take the log of a Gaussian density, you obtain a square, right? Because that's what Gaussian is. You expand your square, a norm square, and you find after one line of computation that this is the thing you have to minimize. Okay, and this minus sign here comes because I want a minimum instead of a maximum. Okay, so that's what you have to do. That's very easy. That's your tensors, your sample, inner product with U. U is your running variable to the P. So that's an inner product of tensors. And you just take the empirical average of this. So if you expand this thing, because you remember that the TIs were my tensors, which were noise W plus lambda U, lambda V, I'm sorry. If you expand this as noise plus lambda V, you get this. Right? That's the noise, which gives you that, the noise, and then that's the signal, lambda V to the P, in a product with U to the P, which is this. Okay? Now look at it. If take V to be E1, what is this thing? This function I have to minimize. Just to simplify, let's take this. This is lambda x1 to the P plus sum of noise, I call them Z, and now you recognize something. That's a spin glass, right? These guys are random. This is a random polynomial of degree P, homogeneous. So this is our old friend, the spin glass. And now you have a spin glass, but you added this very non-random polynomial, which is just x1, also homogeneous of degree P, which is just x1 to the P with a signal in front of it. So you have a random polynomial and a non-random polynomial. One depending on many variables, the other depending on one, let's say. And you add them, and now you're interested in the structure of the minimum and maybe the landscape of this thing. So here, in fact, there is a simple thing to do. You can assume very simply, when you have this sum here, these are sums of the noise that were here. You can, in fact, assume that M is 1. It's the same as having one point in your sample if you change the signal to noise ratio lambda to lambda square root M. So I'll do that, right? So in some sense, the strength of the signal to noise ratio is the same as the size of the sample, right? If lambda is large, it's like the same thing as having square root, as having M large. Okay, so let's just simplify things, and then. So again, if I assume, like I did here, that V is E1, this is what I get, right? This risk is exactly a spin glass plus a very simple signal. So. When lambda is 0, as I said, this is just the spin glass, the spherical Hamiltonian. And we know it's a very complex function. The picture is given here. Does this likelihood function now, which is coming from this statistics problem, does it stay complex when you have a signal to noise ratio? Or when it is large? Right? So of course, if you think a minute, you think, what would you think? Think a minute. Will the complexity of this thing stay serious when you have a very large signal to noise ratio? Right? Having a very large signal to noise ratio means you have, with what I just described, it's the same thing as having an enormous sample. Right? Should it simplify?
Not at the latitude.
Not where?
Not at the latitude.
Which latitude? No, you're probably right, but not at the equator. That's what you mean. Yeah. Perfect answer. That's it. This thing will become simple in the hemisphere. right? Near the signal, this function. But at the equator, it will stay hard. Why is that? Because just look at what the model was. Look at it. If you are here at u1 equals 0, which is the equator, or near the equator, this term here, okay, essentially is very small. Let's imagine you can forget it. Then you have a pure spin. You have a pure p spin. So at the equator, you have a pure p spin, and the pure p spin is just complex. There is nothing to say, right? Okay. So let's see. And so what we have to understand is whether the global minimum of this function will be close to the signal, to check if we have, will be something like this, to check if we have partial recovery or very close to the signal or not. So this function is in fact very complex and has exponentially many local minima. Yeah?
But sir, I thought you said that basically the worst case was if for v equals e1 and that the points around the equator were easier to estimate?
No. No, I didn't say that. Okay. So here you have a function on the sphere, and what I'm saying is that I will say that more precisely, don't worry. But that it will stay complex at the equator, which is the big part. So the picture should be, this is the equator, remember? So here it will be terribly complex, lots of holes everywhere, okay? And then you start at random in the middle of this mess, and you want to go there, right? Because that's where your signal is, okay? Go. So let's continue. Where is the global minimum? Close. So is the global minimum close to the signal of my empirical thing, or is it close to the equator? If it's close to the equator, that's bad news. If it's close to the minimum, to the signal, that's good news. So to understand the topology of this, you use Katz-Rice again. So the random. So as I said, Katz-Rice, this formula that did I write it by the way yesterday? Yes, I showed it to you, right? So you remember that Katz-Rice in fact involves computing a random matrix, which is the absolute value of a determinant, which is of a random matrix, which is the Hessian conditioned by being critical. Okay? So if you do that here, if you do it for the spin glass, as I said, what you get is the random matrix is essentially a simple translation of the GOE. But here we have a signal. And so, of course, the Hessian here at criticality will be a rank 1 perturbation of the GOE. Right? Typically, in the example I gave you, it would be a GOE matrix. And in the top corner, you would add a number. Okay? So what happens when you take a random matrix? So if you know a little bit about random matrices, let's take a GOE. You know that the spectrum of a GOE is a semicircle. Now if I add a rank 1 perturbation, so that's what I'm describing here is called the BBP transition. If I add a rank 1 perturbation, do you see something? So the answer is not always. It's possible to add a rank 1 perturbation, and the bulk here eats the outlier. Right? So you add a rank 1 perturbation, an eigenvalue, let's say, that would be, you add an eigenvalue which is, let's say, here, it won't get out. You won't see it. The bulk of the spectrum of the thing with a rank 1 perturbation is exactly the same as without a rank 1 perturbation. So there is a threshold above which you see an outlier. So you have 3 regimes. When you add a rank 1 perturbation, either it changes nothing to the edge here or to the bulk. Of course, a rank 1 thing cannot change the bulk. That's obvious. You have n eigenvalue, a billion eigenvalue. One will not change that, but it could change the edge. So there is a regime below which this perturbation does nothing, above which it comes out, and here it will fluctuate Gaussianly. And there is a transition regime here where it will fluctuate, we will change the fluctuation of the top eigenvalue. For those who know, this is a Tracy-Widom distribution. It will be a modified Tracy-Widom change thing. This was what this BBP thing did. Okay, so here you have a random. So when does the top eigenvalue of this spike GOE get out of the bulk of the spectrum. This is the BBP transition. There's a long series of works. This started in 2005, and this work was Jinho Baik and Péché, hence BBP, continued in many, many things. It was an interesting, this question was asked by Ian Johnston from Stanford. It was, the motivation was statistics. It was BBP. It was not, it was PCA. So we're coming full circle back to statistics here. Statistics always, I like to be provocative here. All the big things that I've learned in physics, they always existed before in statistics. Right? Always. Random matrix, for instance. It's Wigner, right? No. It's Wishart 25 years before. So every time, just a piece of advice, new cool thing, look in statistics. Okay, so the important result here is a large deviation principle for the top eigenvalue, which was proven by Milan Maida in 2007. This is what we use here. Okay, so what do we find? The total complexity of this thing is always exponential in n, because again, close to the equator, the function, as I said, is close to a spin glass, so it is very complex there, whatever the value of the SNR. When lambda is larger than a certain constant 1, what you see, when lambda is smaller than 1, all the critical points are at the equator. So your function sees nothing related to your signal. When lambda is larger than a constant, which is 1 here, you see a ring of critical points appearing at a positive latitude. So here, you would have critical points here. And of course, along those critical points, you would have the minimum, the global minimum, which is your estimator, the maximum likelihood estimator. The number of critical points in this ring is not exponential, right? The complexity, the exponential complexity is 0. You can compute everything, okay? Here you have exponentially many. Here you may have polynomially many, okay? That's the topology. Oops. When lambda grows, when the signal to noise grows, you have what is called topological trivialization, which means that the number of critical points that you have here, the important critical points, the ones that are close to the signal, again, the number of critical points you have here becomes 1, right? And it's just the absolute minimum, the thing you want to find. So your landscape here becomes trivial. In this thing, you have only 1 minimum, and it's trivial, okay? You still have this complexity here. So here the landscape will be very simple, above this topological trivialization threshold, but you still keep the mess outside, okay? The number of critical points in this informative region, which is this hemisphere, can be computed sharply, and when lambda is large, the complexity in the hemisphere becomes trivial, as I said. There's only 1 critical point, and that's the absolute minimum. So again, when you are in this, so that was answering a question here. When you are in this region where your lambda diverges with n, you are in a completely trivial region in the informative region. In this hemisphere, the landscape is just stupid. It's just you have 1 minimum. It's very simple, right? So that's not the problem. So the descent phase, when lambda is large, is plain vanilla. There is nothing hard, right? The really hard problem here is to escape the equator, what I call escape mediocrity, right? You start from here. Once you get there, going down will be simple. But the real problem is to go from here to there. Yes?
So just so I'm understanding correctly, so at first it may seem counterintuitive that as the signal gets stronger, it's actually much maybe harder to start in like a good area because the ring moves towards the pole, right?
No. But you start from here. So you start here, right? Yeah. What happens here when the signal gets stronger is that the landscape inside this little thing, which is here, this big thing, becomes simpler. So that's perfectly intuitive.
I see, but sorry, just so I'm understanding. So this ring that's drawn is like some...
This one?
Yeah, there are some critical points in here that are good.
Yes, but when lambda grows, this ring comes up.
So it's like easier to find some of these like local minima paths.
If somebody tells you start in this hemisphere, it's very simple to find. That's what I call the descent phase. Okay? The hard part is to get away from here. Because when you start at random, you start from here, at the distance 1 over root n or whatever. Okay, so the hard part is to what I call escape mediocrity. Your algorithm, if it stops here, the answer is mediocre. It's not better than random. As soon as you do better, you escape mediocrity, you're not mediocre, but just your algorithm is just a little good, then it's obvious to become a super good algorithm. Okay? So the descent phase is clear. The hard part is to escape entropy. And if you do it like this, sure. Okay, so now, if, as I said, as I answered, if you had a warm start, that is, if you started from the equator, from the hemisphere, then the topological complexity could play a role. Now, what would happen if I started from here? Then, of course, I would not need lambda to diverge. Lambda could be finite, and then here I could have many critical points. And then what I would do is come from here to there, let's say. And then I could end up in the wrong, I could end up in the, maybe not the lowest minimum, right? If I'm below the topological trivialization thing. So this could happen. This would be an important problem. The topological complexity would play a role if you had a good start. But you never had a good start. The probability of a warm start is exponentially small. Okay? All right, here's the result. Where's the question? Yes.
Just to connect this with what you talked at the beginning with pure thin glass, because there, if you started on the average, it was easy to go to this point, no? This E infinity point.
But here too?
But this is still in the equator.
Yes.
And where in that line, where do you escape the equator? When you're close to the global?
Here, the whole thing is the equator.
The whole thing.
Because I don't have a signal there. So I cannot put a signal. If you add a direction of the signal, then you're doing this model. Okay? So here's the theorem if you want to look at it. It's a long time ago now with Andrea Montanari, Song Mei, and Michai Nika. Okay, so it gives you the complexity result, the need complexity. 1 over n log expectation of the number of critical points given by some variational formula, which you won't remember, but here it is. Okay? And this is obtained through this large deviation principle for the top eigenvalue of. You have an explicit result like that for the number of local minima, and the results show this interesting transition that I was just describing. So when lambda is smaller than a certain value, there is an exponential number of critical points in a band here, as I said. Oh, I'm sorry, in a band here, the equator, and nowhere else. Then at some point, you get, so the band initially grows a bit, and then at some point, when lambda is between lambda 1 and lambda 2, you have a sub-exponential number of critical points here at a positive latitude. But the minimum is still here, which means that if you could find the minimum, your maximum likelihood estimator is still bad. Right? Then, when lambda is larger than lambda 2, the minimum is here. So now this is good news. The minimum is correlated with the truth.
Lambda 2 is what you put?
I forgot that's the threshold, yeah. Lambda, here's the answer. Lambda 2 can be checked to be the IT threshold, so I decided it was 1. So when detection is at all possible, the maximum likelihood estimator does it. This is the reason why we had this, right? When lambda tends to infinity, this latitude, as I said, goes up. So we have a asymptotic strong recovery. Yes?
And the lambda 1, between lambda 1 and lambda 2, this appearance of new critical points, it does not contradict the fact that we cannot even detect the fact that
because you don't have, this is the fun part. This is really, I mean, this is a very good question. This twists your mind if you think of it. Because you're looking at this function, it has plenty of local minimum, whatever. Critical points, sub-exponential number, but here, which means in this tiny hole, but you can find them, right? I'm asking, the minimum is still here. The maximum likelihood estimator still performs poorly because the minimum, the global minimum or maximum is here, right? So you could say, yeah, but the thing contains the information somewhere. Yeah, how do you find it?
I thought the IT threshold was, I am able to say that there is information.
Yes, but the IT, I'm sorry?
I thought the IT threshold was below the IT threshold. I'm not even able to say if there is information.
And
yes, but it's, again, so what happens here is that okay, it's a more complicated answer, but when n goes to infinity, this thing does not contribute. Because, we have a sub-exponential number, and you have an exponential number here. So in fact, again, the limit is, so what you're saying is that in the way there may be a secondary IT threshold, like the way this limit goes to 0 may depend on n in a different way. You're right. Okay, so the optimal threshold for this has been obtained in this thing. And so the real problem that I want to really emphasize is that is escaping mediocrity. Okay? And now, oops. So the question is, okay. So how does it happen? Now let's look at this. So we are here. Let's look at this picture. You start at random somewhere in the middle. And you want to know, so you look at your dynamics. Let's say the one you want. Gradient descent, gradient flow, SGD, Langevin, whichever. Everything, what I'm saying will be true for all of them. So you start from here and you want to go there. Your dynamics, of course, is typically a gradient, and the strength of the signal gives you a force which pushes to this, right? Because remember, it was lambda, you had this term, right? So that's the important term. When you take the gradient, this thing will move you in the x1 direction, right? Which here corresponds to climbing to the North Pole, and here corresponds to going there. Okay? So how does this work, right? So again, you could think, any optimization in finite dimension, any statistical physicist I know before they think about this type of thing, you could think, yeah, the problem is you will fall in one trap. You have a million traps, exponentially many traps, right? And then once you fall in the trap, it takes very long to a deep well. It takes very long that we know exists, because at the equator it is a spin glass. So once you fall in one of them, then your algorithm is dead. I mean, you have to wait exponentially long to get out of it. Okay? So again, because I already prepared for that, now you know that what I'm saying is just absolute nonsense. Right? Because when the signal-to-noise ratio in lambda is large enough, in fact, you just don't fall in the traps in these time scales. In the short time scales, you don't fall, you don't find the traps. Right? The devil is not always stronger. Right? So you have all these bad things, but your algorithm will not see them. Okay? In the phase where it works. When the signal-to-noise ratio is not good, when is not strong enough, then you may find one of these traps and then spend very, very long in it. In the very, very long run, you will get out and find but your algorithm is essentially dead. So that's how what I just said was the refutation side. The other was the positive side. Of course, you have to prove that you have a sharp boundary between them, which is n to the p minus 2 over 2. Okay? So that's what's happening here. If the drift induced by the signal is too weak, the algorithm will linger too long. If this drift here, which is given by or this force, if you want, which is given by the strength of the signal, L lambda, if this is too weak, then you will linger around in this thing for too long and you will fall in a well. Right? But if this thing is strong enough, you will zoom there, and then you will not find, you would be very unlucky if on your path to the hole you had one of these deep wells, right? And in fact, it doesn't happen. So for this thing, we first studied Langevin dynamics and gradient flow with Reza Gheissari and Aukosh Jagganath, who are have been my collaborators for a long time on these things. And okay, it's done for a more. And then we proved that the Langevin dynamics and the gradient flow started for a random initialization converge like that. Okay, we also have a refutation starting with that, and this is done in more general context. Okay.
Sorry.
Yes.
And just the magnitude of this force, it has nothing to do with the landscape.
That's lambda. That's essentially given by lambda, the strength of your. You had this. What I say force is this. If you take the gradient of this, right? You have the gradient of your spin glass. But you also have lambda p x1 to the p minus 1.
And large means it has to be greater than?
That's the right threshold that I gave here, that I, depend on how I normalized everything. Right? But the threshold is exactly this, story here, n to the p minus 2 over 2. Okay? Good. So, so indeed, what I'm saying here is that if you don't have a strong enough threshold, a strong enough lambda, then you will have dynamics in this very complicated landscape, and then you will have aging and all sorts of things, which of course, for computer scientists, for machine learning people, is totally irrelevant. Right? That is, as soon as your thing takes too long, you just stop the machine. You don't wait for this to do this nice thing of aging and all.
This is for Brownian logic. So if I made it active, it could do a bit better.
I bet no.
No,
but I'm ready to put the money. Put yours. I will take it. Because all the local algorithms stop here. Then, if you do something smart, like explain SOS hierarchy, whatever, maybe you can come down here. If with active matter type things you go below this, I'll give you my money. I'll be happy. Okay. So, let's go back to this question of how do you escape mediocrity, this story I'm saying here. Okay, so all that was, is it possible, let me come to this. Is it possible to escape the initial entropy in short time? That's the real question. So here, let me explain this in a simpler model, right? Not the tensor PCA, something that everybody can do with a simple, yes?
I was just wondering, because if I understood correctly, you said that if the signal to noise ratio is greater than this np minus 2 over 2, then we're in the region where there's only one critical point, and that's the signal.
As soon as lambda is large enough, even before that, yes.
I was wondering if there was a topological interpretation of the sort for np minus 2 over 4.
No. Okay, I was not clear enough. The threshold of topological trivialization is lambda finite. So way before that, lambda large but finite. Okay, there is so it's way before that. In all these regimes, the topology in the hemisphere is trivial. Okay, so the real hard part is to escape mediocrity. Okay, so now let's think precisely with the needle in a haystack. Okay, so normally the needle in a haystack is done on a cube, but here I will do it on the sphere. Right, so you pick the sphere, you take the simplest possible exploration, random exploration, let's say by Brownian motion. If you want to think of on the cube and random walk, it would be the same. So you start from a random point. And what you want is to get to a given point, let's say the North Pole, 1, 0, 0, 0, 0. So you start at a point at random, and you say, and here there is no signal, no nothing, no complexity, the landscape is just flat. Okay? You start at random and you want to know how much time it takes to come to the North Pole. All right? So the random initialization is the region of maximal entropy, near the equator. That's what I call E. Right? Because if you start at random, it will be orthogonal to this. So you start here and you just do Brownian motion. How much time does it take to get here, or to get to a little cap around the North Pole? Right? So again, the uniform measure, if you look at it like this, now forget all this complexity thing. The uniform measure, the thing you're trying to find is tiny. The measure of that is exponentially small. And it's very easy to see, so this is what I'm describing here. It's very easy to see here that, that the time to get there is exponentially long. Right? So escaping entropy, as soon as you've got here, going from here to there is not that hard. But escaping entropy, escaping this very large volume, is of course, even without any trap, any complexity, any whatever, is exponentially long. So we should not confuse these two questions. There is the topological complexity, and there's the entropy. Okay? So escaping mediocrity, even in this context, is long. Now you could say, okay, but this is a stupid thing because I have no signal. So you could add a signal. You take a Brownian motion with a drift that push in this direction, right? Here, this drift. And what is the strength of the drift that I need to find this little thing in finite time? It's exactly the same. So if I had done this stupid optimization problem, which has nothing to do with anything, I would find the same answers. Okay, so let's explain that. So consider a more reasonable algorithm. I take the Brownian motion with the drift. And the drift is given by your gradient of constant times x1 to the p, which is this, or x1 to the k here. Right? So I put a drift that pushes to the North Pole. How much time is needed now, depending on n, of course, the dimension, maybe the constant, maybe k. As I said, if you like discrete problems better, take the random walk on the hypercube, on the vertices of the hypercube, plus or minus 1. You start from a point at random, and you want to end up with everybody 1, let's say. How much time does it take if you don't have a drift? To exponential in n. Now, if you add a drift, that is, when you do your motion on each spin, you just throw a coin which is biased. Right? That's the same kind of question. All that is completely elementary. Right? I'm not doing hard things here. So the problem, again, is that the random initialization is at x1 equals 0. So the gradient of this, x1 to the k, when you compute the gradient, it's x1 to the k minus 1. Right? Forget the constants. When you start very near 0, your x1 is not, if you started really at x1 equals 0, then you don't move with a gradient flow. But if you start very near, like in this little thickness around the equator, it's natural that the gradient force will not be very strong, because it's x1 to the power k minus 1. And so you have three cases, three regimes. The easy regime, when k is 1, which means you really have a drift, because power k, x1 to the k minus 1, when k is 1, is a constant. So when k is 1, you have a strong force here. Right? So you escape quickly. That's easy. Critical is case 2, because then you have x1 to the k minus 1 is x1. And hard is k larger or equal to 3. Okay? Of course, in our p-spin models, k, which is here p, is larger or equal to 3. Right? So we're in the hard regime. If you do the computation with this stupid model, you compute everything right. Okay? So, of course, if you look at this stupid model, you see that, in fact, you don't need to know that this thing is in a sphere. You can project in one dimension. You can project here on this dimension, on the latitude, on x1. That's the only thing that is important here. And if you look at that, you will see that you have the projection in x1, because then your gradient of x1 will be in this direction. The projection in x1 will be an autonomous dynamics. You would have the gradient of x1 and then the projection of a Brownian in one direction, which will be a Brownian. So you would have autonomous projection. If you think a minute, this is very unusual. If I give you a dynamical system in dimension n, when you project it, it's not autonomous. Otherwise, life would be so nice. But it's not like that. So here you have a situation where you have a one-dimensional projection which is autonomous, and the classification of whether it's easy, hard, or critical is just this number. So okay, so I won't do that. Where am I here? Here it is. I'm sorry. This was absurd. So the setting I just told you. Now you could ask. So I showed you the spin glass with one, with the tensor PCA, one spike. And we had this one-dimensional projection which is autonomous and one number which describes everything, this exponent. Right? Now you think a minute and you say maybe this happens with very different statistics models or machine learning models, where now we don't have the spin glass story. That was what made the link between spin glasses and our story, right? Where you don't have the spin glass story. So again, you have your loss function in general, and maybe the structure of the loss function is that, in fact, it depends, the population loss depends only on one dimension, right? Like we have here, the population loss. What is the population loss here? That's the empirical loss. The population loss is you take the expectation of that. So this disappears because the spin glass was centered. So the population loss is just trivial. It's just this. right? And it's a function of one variable. That was why this thing was doable. So let's imagine in general that your population loss is in fact a function of one variable, which of course the hard part, I hope, okay, maybe I should insist on that. If I tell you the population loss is this, the model seems stupid. Except that you don't know which direction, you're not supposed to know it's x1, right? You don't know the vector v. That's what's unknown to you, okay? So, but you could know that in fact it depends only on one projection. So in general, this happens a lot. And so this is what we did in this work. Here's all sorts of problems of statistics and machine learning, which are rank 1, like this. So spike matrix and tensor model, this is what I just described. GLMs, phase retrieval, single layer teacher-student network, two-component mixtures of Gaussian. All these are very classical problems of statistics. And all these have this rank 1 structure. Okay? And so for these, we call this exponent, we called it the information exponent. Right? So when the information exponent is 1, the algorithm works in finite time. When it's 2, it works in log time. When it's 3 or more, it works in polynomial time with this exponent. Okay? So let me explain this very briefly in the 5 or 10 minutes that are left. So this is online, OGD means online stochastic gradient descent for rank 1 estimation and the information exponent. So we have SGD, or online SGD, which I remind you was this, right? You have the position at a certain time, you do a step size delta, take the gradient with your last data point. And here, of course, I put it in the sphere, so I just normalize by, I divide by the norm to stay on the sphere. So that's online SGD, the simplest version of SGD, right, with very, very small batches. And I start from whatever distribution at 0. So, okay, I will not be under certain, let's say, I won't get into these technical assumptions on derivatives and whatever, but we can prove that the online SGD recovers the signal partially, so you climb up like this here, in time t equals O to m with the right choice of alpha, which is the ratio of m over n, and of delta, which is the step size, which is in your hand. You choose the step size. So this right choice depends on the geometry of the problem, and in particular on this information exponent, which I call k, here capital K, I don't know why. So here's what you find. So here's the structure. So this is the, I assume that the population loss, as I said, is a function of one variable, this m of x, which is like the latitude here. And the information exponent is the number of vanishing derivatives. Okay, that's as we said before. Right? It's 1, 2, or 3, whatever, at 0. And then here is what, so I have to pick my step size between alpha to the minus 1 and alpha to the minus 1/2. Remember, alpha was the ratio between the number of data and the dimension. So the step size has to be chosen depending on the dimension and how much data you have. Once you do that, then you have the following classification. The simple model, information exponent equal 1. So you need alpha to be larger than 1, which means, remember that the number of samples must be larger than the dimension, which seems reasonable. Then that guarantees that after alpha n steps, because remember here in this online SGD, each step corresponds to one data point. Since I'm not reusing data, the number of steps I do is the size of my sample. Right? So that's this m, it's like the time parameter in my thing. Then this the latitude converges to 1, right? So things become very good. Now, when k is 2, what you need is that your alpha should, so m divided, so the size of the sample divided by the dimension should diverge like log n square, and you have the same guarantee. Okay? And when alpha is, when the information exponent is 3 or more, like we had in the spin glass or Tensor PCA case, you need n to the k minus 2, right? which after a little transformation, k was p, so this would explain this n to the p minus 2. All right? Maybe you don't remember why there is a square root, but remember I was saying the signal to noise ratio, in order to get it in terms of the data size, you had a square root of m. That explained the square root. Okay, so just trust, we were able to follow these powers, and this is what happens. Okay, so this tells you precisely that this information exponent, even when you have this very nice structure where your problem, which seems very, very high dimensional, in fact depends on only one dimension, that you have three possibilities. It's easy, critical, or hard, depending on the information exponent. Okay, but still hard means, it's still polynomial. Right? This alpha larger than n to the k minus 2, it still tells you that the number of data points you need is polynomial, not exponential. Right? The number of steps you have to do in your online algorithm is polynomial. Right? So it's harder, but still not exponentially hard. Okay. And you also have a refutation result, that is when you're on the wrong side, then when alpha is less than 1, or much less than log n, and much less than n to the k minus 2, you can prove that the online algorithm doesn't work. That is, you stay stuck at the equator. You stay stuck in the mediocrity. Okay? Good. So this applies. So here's an example, the first example of neural net, and I will stop there. So you all know what a neural net is, right? Yes? No? So here I take the the simplest example of a neural net, which is just single hidden layer. So you all know what that is. You have nodes, and so here it's just one layer, so it's just this. So what you do here is you enter your data, x, and here you have weights, which I called A, right? And sigma is an activation function, so which you choose. It's a nonlinear function. So let me explain. Okay, maybe I don't need a picture. What is a neural net? It's the idea that you can approximate complicated functions by very simple ones, that you obtain by linear and then pointwise nonlinear. And you choose the pointwise nonlinearity. And then again linear, and then pointwise nonlinear, etc. That's all. And the idea is that this class of function, and there is an abstract result saying that this class of function is a good way to approximate any functions, right? So, but of course the hard part in machine learning is to find the parameters, the weights you put on your linear parts, right? That's the. So depending on the activation function, for this very simple case where you take the L2 loss, I take here the L2 norm, that's my population loss. Then for a single layer, depending on the population, the activation function, the choice of the nonlinear thing, you have either the easy regime where the information exponent is 1, or the critical, or the hard. And of course, look at what's happened in this very simple case. If you take sigma, the activation function, to be what everybody uses in machine learning, that is ReLU, rectified linear unit. You know what ReLU is? It's a big word. It's a ReLU function is x plus. Right? So it's this function. Okay, that's very simple. Sigmoid, of course, I guess you all know. So when you take the usual function, sigmoid or ReLU, in fact, your k is 1. Which means that if you take this sigma, it's an easy problem to escape complexity here with this very simple network. If you take sigma to be u square, or absolute value of u, as an activation function, a quadratic activation function, which is the case for what is called phase retrieval, then it's the critical regime. If you take u, if you choose u, sigma, I'm sorry, badly, like the Hermite polynomial of degree 3, whatever, who wants to do that, right? Then it's hard. It's the same regime as Tensor PCA. Of course, nobody would, why would you, here again, it's the pervert side, it's the theoretical computer science side, saying, you know, I want to find a hard thing. Of course, you don't want the hard thing, you want an easy thing, okay? But again, in all these algorithms, which are now very far from Tensor PCA and spin glasses, you had the two phase, escaping mediocrity and then the descent. I'm still on the sphere. And again, so the hard part is, or possibly hard part is to escape mediocrity, depending on the information exponent. But then once you've escaped the mediocrity, the descent phase is fast and trivial. Okay, so that's not hard. Okay, so that was rank 1. Now you could ask yourself, and I will not do that. Okay, so that was cool. That was very well accepted by, we did abstract nonsense mathematically from spin glasses, Tensor PCA, then Tensor PCA has this rank 1 structure. Maybe there are other things that have rank 1 structure. We find the exponent that explains everything. But then you say, come on, nature cannot work in rank 1. So maybe for serious problems of machine learning, in particular this classification of cats and dogs and flowers and whatever, classification of a mixture of Gaussian, which is the central task of learning some years ago, maybe, so again, this will define, I could spend time, but this will define, of course, a dynamical system in high dimension, right? Because your network has very many parameters. But maybe those things work in low dimension. Maybe not dimension 1, maybe dimension 17, right? Which is still much better than dimension 10 to the 9. So we started from the principle that things cannot be too complicated, right? Which has a name, of course, in European philosophy. It's called Occam's razor, right? So, you go back to the idea that things cannot be that complicated. So it's just an optimistic point of view. And so if you're optimistic, you do math like Bourbaki did. This is what we did. That is, you decide, okay, what would it take for this to work? This idea that, in fact, those crazy dynamical systems work, in fact, in low dimension. So you do it axiomatically. Here is what we would take, blah, 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 blah. And then under these conditions, the dynamics will be in low dimension and they will be autonomous. And then you reduce all this problem to a dynamical system in low dimension, which now can be much more complicated than dimension 1. A dynamical system in dimension 1 is not very complicated, but in dimension already 2 or 3 can be horrible, right? So you reduce this to a question of dynamical systems. Great, but of course, then you have to find examples, because Bourbaki is cool, but you need to find. So I will show you examples of that. So I will first introduce this summary statistics and effective dynamics. That's what it means. Summary means this autonomous projections, and the effective dynamics are the dynamics of these autonomous projections. This dynamical system can be deterministic. It can have a random noise. It can be simple. It can be horrible. But the important thing is to realize that it should happen in essentially all interesting problems. And every time we try, this is what happens. But now, the question that we'll see in 2 days or 3 days is the following. You have simple models in which you guess what this projection should be. Right? For instance, in Tensor PCA, you guess what it is. It's, of course, the direction you want, the direction of the signal. But now, in harder problems, and I will show you some serious problems, in harder problems, you don't really know. So how do you find this important direction on which to project and find a dynamical system? There's only one tool, and that's the BBP transition, right, that we saw there. So here, but here we were looking at this for the critical points, but you don't know where the critical points are. So what you can do is run your algorithm, and along the trajectory of your algorithm, look at the Hessian. And it should dynamically develop, if you're lucky, if you have enough signal-to-noise ratio, it should develop a BBP transition, a few outliers. Then the eigenvectors corresponding to that might define a nice projection on which the dynamics could be autonomous. Right? And this dynamical system is where the signal is, everything else is noise. Right? If you can do that, you've done PCA at a high level. And in fact, I'll show you that next time that this works, in particular for the problem that motivated this whole story when we discussed with Yann Lequin at the beginning, which is classifications. Okay? Cats and dogs and flowers. All right? But the story is a little complicated. So next time I'll come back to this whole thing. Okay?
Okay. Thank you very much.
dimension is for large in the matrix, but if you are in low dimension, what is large?
The dimension is very large. N is large. The dimension of your parameter space. What is not large is precise in the BBP. In this picture, here I had one outlier. The dimension of the outlier here is 1. That's not large. But this is large. So this is what we have. What you have is you're in dimension n. Your Hessian may be a very complicated random matrix, which will not be a semicircle. The spectrum will be whatever. You have 10 to the 9 eigenvalues. And you have 17 outliers where, in this direction, things are cool and carry information.
Okay. So when at the end you say low dimension, you mean few outliers?
Yes, 17. The rest is junk, right? Like here. The rest are all the directions that are not in this direction. They're all these directions.
Yes. So for the analysis, you've assumed one value of lambda. But imagine if your data is collected in different laboratories with different signal-to-noise ratios. So if I put an index on the lambda, would it be interesting to sort of generalize?
Yes, there is 145 pages on that by Cedric Gerbelot, Vanessa Piccolo, and myself. And it's the multi-spike Tensor PCA. And yeah, so the picture is more complicated. Here the BBP transition is with one outlier. You may have many. All sorts of crazy things can happen, but you're right. So it depends whether the lambdas are very close or far. So this is studied, yeah.
Okay, great.
Yes?
Just to sketch a little bit, how would the computation of K go for this simple machine learning model? Like, how do you connect the activation function?
I gave you so it's very simple. Again, it's the population loss. So I gave you the population loss, which here is just this, right? You had a formula for it, right? Expectation of sigma of AX in the simplest case minus sigma A star X, whatever, square. You have a function. And now you compute how many. So clearly in this context, you have first to identify what is the proper direction. And K is just the number of derivatives in this direction at 0 at the equator, which are 0, right? So it's just a calculus in one variable.
Okay, so let's thank again Gérard.